Welcome everyone to a bit of a different video where we'll be recreating Conway's Game of Life. So basically, at the time of recording this video, I just uploaded the part 2 of the QR code series on the main channel, and well, seeing that it's going to be another couple of months until I upload the next video there, and I'm not even sure if it's going to be the part 3 of the QR code series or I have some other ideas that I'm working on, but either way, it's gonna take some time until I get the next video up there. So I thought to bridge the gap between the videos, I'll bring this channel to life, where I'll do some live coding, bit smaller project that are in a more, or like I should say, in a less scripted or less edited way. And as I said today, I thought very fitting to the first video, we're gonna be creating Conway's Game of Life in Python. So now actually before I explain the game, in my environment here, I'll be installing Pygame because this is the module we're going to be using to create the window and to have a game loop and everything. So that was actually quite fast. Now let's maybe quickly explain this Game of Life. Now I'm sure many of you are familiar with it because it's very popular in computer science or in maths. But as you can see, we have these cells here that are either grayed out or this yellow color here, so either dead or alive in the context of life. And through some logic and some rules that we're gonna get into later, these cells produce these very almost organic looking patterns. So maybe I can stop it and maybe here I'll draw, for example, this shape. This produces an interesting pattern, and it's in a way looks chaotic, but then also ordered again, because for example, this pattern always, well, no, never mind, I've broken it now, but here, for example, this pattern always produces these gliders and so on. So this game has the simulation is very intricate patterns and all of these configurations. And even though it runs on very simple rules. So today I'm going to be trying to recreate that. All right. So, before I actually get into the rules and into the logic, so I have the Wikipedia article here where we have all the rules, how these cells actually interact with each other. Before we get into that, I want to get the basics done and at least for now just have a Pygame window open and a game loop running. So for this, I have a cheat sheet here because I still can't quite remember the full setup what we need to put in to get a basic game loop running. So we do pygame.display set mode, and here we need to input the dimensions of our screens. So I'm just gonna be calling it width and height, and we're gonna define them. Let's do 900 by 600 pixels for the screen dimensions. And yeah, then we're going to be introducing a clock, pygame.timeClock. This is going to be to limit the FPS. Okay, and now we can get onto the event loop. So while the game is running, we are going to be polling for events. So we're going to do for event in pygame.event.get. Event.type. So basically what we need to set up first is to be actually able to close the window. So I'll poll for the quit event, and if I quit the window, we'll set running to false, and then so we're gonna exit the loop, and once we exit the loop, we're gonna just call pygame.quit. Yeah, okay, just before I forget, I'll just put in the clock.tick. Let's just limit it to 60 FPS, just before I forget that. Okay, so if I run this window, yeah, there we go. We should be getting an empty Pygame window that is about 900 by 600, looks about right, yeah. Okay, so the first thing I want to do, if I get the Game of Life back up here, is I want to be able to draw this grid here, and I want to be able to draw these cells again, we're going to talk about all the logic later. For now, I just want to get all the visuals done, and then we can talk about the rules. Okay, so for this, what I'll do is we'll make a class called, board init. And we'll need a board width and the board height. So basically, let me just write this up, board width and self.board height is. So basically, as you can see on this website that is running the game, we can scroll around, we can even zoom, and it's seemingly infinite. I'm not going to be implementing that today. That's going to be way too much work. So we're just going to limit it to like some static amount of pixels in the X direction, the Y direction that we're just going to input here. Okay, and then obviously we'll need to keep track of the grid, or like the cells itself. So we'll have a self.grid. And for this, we're just going to have a 2D array. So, well, since the cells only have two states, so like alive and dead, we can denote them with just a number. So we can have 0 for dead or 1 for alive. So like true or false, alive or dead, 1 or 0. You see this, it has this binary nature. So we're just going to be initializing the cells with a 0 for now, because at the beginning I want them all to be empty. And we do it for underscore in range self.board width, and for underscore in range self.board height. And this should give us a 2D array of zeros, basically. Okay. Before we implement this, oh damn. That's not, there you go. So before we implement this in Pygame, I just want to test it out. So we have a board is a board. Just for readability, we'll make it, I don't know, let's say 4x2. And then I'll print the board dot grid real quick to the console. And yeah, there you go. So we have this 2D array of all zeros, basically. All right, that seems to work well. Okay. So, this is where all the logic is going to happen. So, like, we're going to be manipulating these numbers in the grid. And now we need a better way to display them than here in this terminal. So, what we'll need is a draw function. So, draw self. Now, because of the nature of this game, we can draw the entire board each frame, or like each generation. Like we can draw the entire board. We don't have to actually individually update cells. So we're just going to have one global draw function for the board. And for this, we're just going to be looping guys, we're going to call it J for J in range of the height and for I in range of the width. So basically we're going to be looping over every entry of this grid. And then we're going to be drawing a rectangle. And in Pygame, that is actually quite simple. Let's actually forget about the loops for a second, and let's just get a rectangle on the screen. So what we can do in the draw, pygame.draw.rect, and then it needs a surface. The surface is going to be obviously our screen. Then it wants a color in RGB, so we can just input the tuple. Let's just make it red for now. So 255, 0, and 0. And then we need a rect. And I'm pretty sure we can just input a tuple here. We don't actually need a Pygame rectangle. So the first two coordinates are where the top left corner of the rectangle should be. And then the next one are for the dimensions, width and height. So let's do 100 times maybe 200 pixels. Just to test it out. So here in the event loop, we're gonna be doing board.draw, calling this every frame. And let's see how that looks. Let me actually close the old window, and there you go. No? Okay, nothing actually happens, even though we are calling the function here. But there's actually a good reason for that, because yes, Pygame is drawing the rectangle, but it's not updating the screen. So what we need to do is pygame.display. I think flip. If I run the program now, yeah, there we go. We see our red rectangle at 50-50. Okay, so just like these rectangles, we're going to be drawing our cells now. So let's, I think actually we can keep this basic idea. We're going to bring back the loop. What we're also going to be needing is a cell size. So basically, this board has, for example, here 4 and 2 entries, or 4 by 2 entries, and while the screen that we displayed on has 900 pixels by 600, so we need to kind of translate between the two values. And for this, we'll just do the width of the screen divided by self.board by the width. Now, okay, of course, for this, we would somehow need to make sure that the cells always have a square, always square, even when, for example, alternatively, we could also define it by height over self.board height. And these obviously would have to match for them to be square and so on. I think we're just going to ignore this issue for now and just stick to nice numbers. So, for example, here we can do 90, or like 9 cells by 6. So each cell is going to have a size of 200 in this case. So yeah, I think we're just going to ignore it for now. Okay, so we have a cell size. And then we go through the screen and we actually need to draw the rectangle. So let's actually get this out so it's a bit more readable. So rect is going to be a pygame.rect. So the width and the height is the cell size that we just calculated, and the position should be dependent on which cell we're looking at. So the x should be I times cell size, yeah, and the y should be j times cell size. Okay, and if we run this now, okay, we actually get a red screen, and this is actually now different from what it was before, or different than just filling the screen, because we're actually drawing each rectangle on its own. To maybe better visualize it, what we could do is import the random module, and I think, yeah, we can just make a color and do random.rand int and give it a range for RGB. So we're just going to stick to the red channel for now, but I think that's fine. And if we run this, okay, maybe that's a bit too fast. Let's knock down the, let's just do 1 frame per second. And yeah, there you can see, we actually draw these individual cells, and here they have these colors. So that's actually pretty good. Now, obviously, when they are all the same color, it's a bit hard to see. So if we make them white, 255, 255, and 255, it's a bit hard to see that we have individual cells. So what I'll maybe want to do is give them maybe an outline or something like this. And the easiest, also, let me just copy this out and we'll call the color white, and we'll just define it with this, and same with black 000, just so it's a bit nicer to look at. So this is the cell, and I think we can just give it, so if I maybe just duplicate this down, we'll do the color, make this black, and we can give it the width and I'll make it, for example, 5. Yes, and this draws basically an unfilled black rectangle with a width of 5 pixels. And with this, we can actually see our cells a bit better. Okay, now maybe what happens if we increase this? Let me close the window. Oh, yeah, also maybe bring back the frame rate, because I think that actually even prevents us from closing the window every, like, 60 times per second, because I think then the clock is actually limited, and okay, yeah. Yeah, anyway, let's see what happens if I do it 90 by 60. And now the entire screen is black, because we don't even see our white rectangles anymore, only the outline. So let's make it 1 maybe. Yeah, and then we would see it again. Okay, so maybe we need to do this outline a bit more dynamically. So we have a rect here. Let's maybe also have an outline width, which will be the maximum between 1. So I want always to have at least a 1 pixel of space or of this outline. And maybe say cell size times 0.5, maybe 5% of the cell size. Okay, so here it looks the same, but what happens if I do 9 by 6 again? Yeah, so now it's a much thinner, but is it actually working? Wait, how about if I do 10%? Oh, obviously, I need to put it in. We're still using the width of 1, so I think 0.5% or like 0.5 was fine. Float object cannot be interpreted as an integer. Yes, obviously, 5% of the cell size is not always going to be an integer, so we're going to round that whole thing. Yeah, and now we get this. And I think I'm pretty happy with this. You know what, maybe just to have some nicer numbers to deal with, let's just make it 800 by 800. And then we do 40 by 40 here. Yeah, okay, I think this looks reasonable. Okay, so the first step is done. We can draw our cells now. Now, at the moment, we're all drawing them white right here. We're not actually checking for the state of the cell. So let's implement this. Now, they're all represented through a 0 here, or later it's also going to be some 1s in there, but basically we're going to just use this. So we can have a color. And since it's just a 0 or a 1, we can just do white if self.grid of j of I, else just black. Well, basically everything other than a 0 is going to be interpreted by the if as true, so especially the 1. And if it's 0, then this will fail and we'll just draw it black. So now if I run the code, we should see a black screen if I actually were to input the color instead of white. Now it's black. Maybe let's actually differentiate, because when it's all black, we don't see the outline either. Maybe let's have something like gray and do it maybe 25, 25 and 25. So not black, but just gray. Okay, yeah, this looks good. So now you can just faintly, you can faintly see the outline even when the cells are black. And to see if this works, we can actually go down here to the board and just manually set some cells for now. Board.grid of, I don't know, say maybe 10 and 10. We set it to 1 and maybe something like this. Yeah, and we actually start seeing some cells light up. So these would be the live cells for now, for example. Okay, also what I want to be able to do, maybe just to also make the whole debugging, the inevitable debugging later, a bit easier, is I want to be able to draw these cells with the mouse, not just having to input them here into the code. So what we could do for this is here in the event loop, where we check for events, we can check if event.type is equal to, what was it? Key down, yes. We can do if it detects a key being pressed down. Actually, no, never mind. No, we need mouse button down. I wanted to be able to draw it with the mouse. So if it's mouse button down, if I press the mouse, I want to get the mouse pause. Is pygame.mouse.getPause. And we could maybe print it to the screen, print mouse pause just to see it. So if I click somewhere in the screen, you can see the position there. So up here, it's going to be around 0, 0, yeah? And down here, 800 by 800 something, and in the middle. So yeah, I get the position of the mouse. Now, depending on that position, I want to switch the cells. So the X position should be mouse pause of 0 and Y is mouse pause of 1. But obviously, we don't want to have these numbers. We will need to like convert them to the grid. So what we'll do for this is just, I think, just select both and floor divide it by the cell size. And yeah, okay, for this, we'll need to define it outside of the draw function. So you're going to have a self.cell size. And then I'll have to update that here. Self dot. Yeah. Because then we can just access this here with board.cell size. Yeah, also, so we're floor dividing it by the amount of cell, no. Yeah, okay, by the cell size, yes, that should be correct. And then we do board.grid of Y and X. We just set it to, let's just set it to 1 for now and see if I've actually messed something up or if it works. So. List indices must be integer, not float. Why though? Of Y and X, the floor diff should cause it to be an integer. Okay. Print XY. Oh, okay, so it's really, it doesn't get converted to an integer. Okay, I mean, we can fix that. Okay, interesting. Okay, now it works. Okay, that's interesting. I always thought that floor division also converted it to an integer. Oh well. Okay, but it works now. So now we can set the cells. The thing is, now I can't turn it back off again. So for this, what we'll do here is, again, since it's just a number, 0 or 1. Actually, could I just do not that? And it gets actually recognized? Yeah, that looks good. But is it still a... Wait, let me actually check that. I'm interested in this. Let me just print board.grid. Is it still being seen as a number, or do you turn to like a true or a false then? Okay, maybe I shouldn't have pressed it that many times. Wait, hold on. Let me clear the terminal. Try it again. I mean, I'm not seeing a true or a false, so I think... Oh, no, actually, yeah, no, yeah, okay. It gets but the thing is, it still works because we're using this Boolean logic here. So, but okay, we're not gonna do that. So what we could do instead is just add 1 and take it modulo 2. This should basically invert the bit and without converting it to some Boolean value now. Okay, so close this. There you go. Okay, and that looks fine. Okay. And yeah, I can also turn them back off. Okay, great. So I think with this, we have all the prerequisites done to talk about the logic. Now, again, obviously, the logic is what gives life to all these very complex, this behavior. And the rules for this are actually quite simple. So if we look in the Wikipedia article here around the rules, there is only 4 rules that describe this entire game. So the first one is any life cell with fewer than 2 life neighbors dies, as if by underpopulation, if we want this analogy of life. Then any life cell with 2 or 3 life neighbors lives on to the next generation. And any life cell with more than 3 life neighbors dies as if by overpopulation. So these apply to all the life cells. And then there is one last rule: any dead cell with exactly 3 life neighbors becomes life cell as if by reproduction. So basically these rules are divided into the ones for the life cells, and then here the last one is only for the dead cells. Now, I think the easiest way to actually get an intuition for this, or to understand it, is to yeah, I think I can just do that. Is to just try it out on paper, basically, or on like a board here. Now, what I'll do is I'll create a grid here, maybe something like this. And we're just gonna have a really quick tryout of these rules. So, okay. So this is gonna be generation 0. So this is going to be generation 0, and this is going to be generation 1, and between the two, we're going to have the rules. So I'm going to just maybe use this glide. Actually, maybe let's not make it white here. Use this glider shape. I think this is still, yeah, visible. Now, and now basically all we need to do is go through all the cells one by one and see if the rules apply. So, okay, this dead cell, remember, dead cells only come to life or only change if they have exactly 3 live neighbors. Okay, so this cell has 0. This cell has also 0. And by live neighbors, we mean the immediate neighbors. So if we're looking at this cell, we only mean the immediate neighbors of the cell. So as I said, this cell has 0. This cell has, 1. This cell has also 1, and also 1, and 0, and so on. So these don't change. This cell also has 0. This cell also has 0, and now we actually, oh no, actually it has 1, but whatever. And now we get to a life cell. Now, life cells need 2 or 3 cells to survive. And if it's fewer, or if it's less or more, they die. So this cell only has 1 neighbor, so it's gonna die. And okay, so we can just leave this blank right here. And then we move on. So this dead cell only has 2 neighbors, so nothing happens to it. This cell has only 1. This has 1. Now this dead cell has 1, 2, and 3 neighbors. So this cell is gonna come to life in the next generation. So this one is alive, the first actual live cell. Now, okay, this cell has 1, 2, 3, 4, 5 neighbors. That's too many, so it's gonna stay dead. This cell has 1, 2, 3 neighbors. So since it's a live cell, it's gonna live on. So this one's alive. This cell stays dead. This live cell only has 1 neighbor, so it dies as well. So we'll leave this blank. This live cell has 3 neighbors, so it stays alive. And this live cell has 2 neighbors, so that's also fine, it stays alive. So we get this shape. And then we just need to check the dead cells. So you have 2 neighbors. This cell has 3 neighbors, so it comes to life. And I think that's all of them because you only have 2 neighbors and so on. So you see how the state of the 0th generation exactly predetermines the state of the next generation. And each cell is individually only affected by its neighbors. And I think this is correct. We can actually double check it if we go into the game of life. Oh, maybe pick a quieter spot here. And if I draw this glider shape and just reduce the speed of the simulation, see that it's doing the simulation now. Nope. Well, here. As we can see, this is exactly the shape we predicted from this manual understanding. Actually, the interesting thing about this game is it was invented before computers. So the first, runs of this game were actually done on paper. So it's actually, kind of interesting to think about it, that we're doing it now with the help of a computer. Okay, so basically these rules I want to implement in Python. Now, for this, I'm just going to remove this here. What we need for this is going to be a method to actually first count the neighbors, since all the rules depend on the amount of neighbors. We'll give the board a count neighbors method. And obviously we need to know where we count it, so we give it an X and a Y. Okay, so again, let me just open Paint real quick. Again, by neighbors, we mean the immediate neighbors, also like across the diagonal. So if this cell has the coordinates X and Y, we're going to be checking all the cells around it. So in this case, this is going to be X minus 1, Y minus 1. This is, for example, going to be X plus 1, Y, or here, X plus 1, Y plus 1, and so on. So basically, the way Pygame uses the screen or keeps track of it is the top left corner is 0, 0, and then X increases rightwards and Y increases downwards. So let me just fill out this screen a bit. So there's X plus 1 and Y minus 1. So around this cell, we're going to be checking all these neighbors. And the way we're actually going to do that is I'll have let's call it offset. And you're going to be just the list of tuples of maybe not X and Y, of I and J, or let's call it N and M. It's whatever, actually. Of N and M, for N in range -1 up to but not including 2, for M in range -1, again not including 2, because with this we could just add the elements of this tuple to the X and Y to reach these offset neighboring positions. Let me just print the offset so we can see that this works. So yeah, I'm just going to be calling this board.check count neighbors. For example, at 0, 0, it doesn't even do anything now, so we can just do that. And yeah, as you can see right here, we get 0, 0, -1, -1, -1, 0, -1, 1. So exactly, for example, here this row and so on. Great. Okay, and then what we need to do for X, of and y of in offset, I think I can just unpack the tuple like this. And what we need to do with those is count the neighbors. So we do a neighbor is self.grid at the position y plus y offset and x plus x offset. And then what we also need is like some global counter that counts the neighbors. So once we found the neighbor, we can just add it to the counter, since again, all the cell is a 0 or a 1. So we can just add it to the counter. And obviously then at the end we return the counter. And I think this should work. Now, let me... how are we gonna do this? Yeah, each frame, we're gonna count the neighbors of the cell. Let's maybe do 1, 1. And let's go back to the big view. Like this. Okay. Also, maybe we need to print it out so we actually see it in the console. So, okay, now it says 0, 0, 0, 0. So if I put a neighbor here, we have 1, 2, 3, and if I do anything else, it doesn't really care. Yeah. Now, the way this is set up, I think if I press the middle cell, it also counts itself. So we only should be having 3 neighbors here because obviously you yourself are not your neighbor. So what we need to do here is exclude it from this loop. So all we just do if x of y of is not equal to 0, 0, then we count the neighbor. And I think this should fix it. So 1, 2, 3, and the 4th neighbor is not getting counted. Wonderful. Okay, so now we have the number of neighbors. We can determine this for each cell. And we're going to use this now to make a def next gen method that basically computes the next generation. Because as I said, as we can see here, it works by generations. Now, the naive implementation of this would obviously be to where's the column over here? Is to go through the grid and instantly change it. So the first change was, I think, this cell, that this cell dies in the next generation. The naive implementation would be, okay, this cell, well, there's one neighbor, okay, so it's dead. Well, and I carry on, okay, so this cell stays dead, and so on, so on, so on. But for example, this would change it because now this cell only has 2 neighbors instead of 3, and so on. No, the way it works is basically that it gets written to a buffer, and this is the same thing we're gonna need to implement here. You'll see what I mean in a second. Maybe I didn't explain it terribly well, but okay. So next gen. What we'll do is we'll just loop through the entire grid again. For j in range self dot height, and for I in range of the board width. Just make some space here. We're gonna loop through the whole thing, and we'll need to count the neighbors. Neighbors is gonna be self.count neighbors. Now the the x position is at I and the y is at j. So this is going to be the amount of neighbors we have, or the number of neighbors we have. And now we need to implement our rules. So let's get back to the rules here. The first one, any live cell with fewer than 2 live neighbors dies. Oops. So we're actually going to divide the rules into the live and dead. So if self.grid of j and I if it's alive, we do rule 1. So this is the underpopulation rule. If neighbors is less than 2, self.grid of j and I equals 0. So then the cell dies. Yeah, fewer than 2. Okay. Then we have stays alive is if neighbors is between 2, so it's greater or equal to 2 or greater or equal to 3. Dot grid of j and I, it stays alive, so it stays 1. And if neighbors is greater or greater than 3, the cell dies, equals 0. Okay, and now we just need to, now we just, actually maybe just for consistency, maybe let's have self.if, maybe just to avoid any weird behavior then that I'm gonna have to debug. Let's just do it like this. If it's 0, then, and also I'm gonna call this rule, this is the overpopulation, and this is reproduction, is if self.neighbors, no, if neighbors is exactly 3, j and I comes to life. Okay, yeah, this looks good. Now, what we'll do is implement it here. So each frame, we're gonna do board, actually before we draw it maybe, board.nextGen, we're gonna call that. And let's run this code and see what it does. List index out of range. Oh yeah, obviously. What we need is we're doing these offsets here from -1 to 2, like to 1. We're doing these offsets here. We're going on the diagonal. No, there you go. We're going up left, up, and up right. Obviously, we need to account for what happens at. Actually, but that should. Actually, so what I'm saying, we need to account for what happens if we're at the edge of the screen. So if this screen only goes to here, there is no neighbor here to check, or this neighbor here to check. But actually, now that I think of it, that should just go to -1, because if this cell is 0, 0, this is -1, -1, and this should just access the last elements of the array. So why would we get a list index out of range? That's a good question. Go through the neighbors. Iron range board width. It's interesting. Well, let's just print these and see where it actually goes wrong. Let's see where it goes wrong. -1.8. Okay. So the same thing I just explained, but basically for the other end, what happens here? Because if we're at the top left edge of the screen and we go to -1, -1, that's not an issue because that gets interpreted as the last element of the array. The issue is if the screen is here and we are at 7, 7, or actually, wait, no, that's x is 7 and y is 0, whatever, and we want to check outside, then we run into issues because that's going to be 8. So this is actually the issue. So what we actually need to do here is, so if it's not 0, 0, we need to also ensure that it's within the grid. So if 0 also we're just gonna maybe call it x new is x plus x offset, and y new is if x new. So basically it just needs to be smaller than the width, and 0 is less or equal to y new, and that should be smaller than the height. Okay, so indent this, and this is y new and x new. Okay, and I think this should fix it. Okay. Now the screen is black and nothing happens when I press, but that is because the game is too fast. So maybe let's limit it to 1 if I think 5 should be fine. Yeah, no, it still gets overridden too fast. So what we'll do instead is maybe have the board has a self dot simulating, maybe. Let's force it first. And then in here, in our event loop, we can also check for if event.type is pygame.keyDown. So if I press a key now, for example, and I'll just make it maybe space, pygame.k space, print. So for example, now I should be able to, yeah, if I hit the spacebar, I get a hello. And in here, I'll set the board.simulating to not board. So basically invert it. So, wait, let me just retry this. So right now we're not simulating, so I can just, I should be able to draw, really. So it's false. Why can I not draw then? Oh, is it maybe because of frame rate? Let's put it down to 60. I'll put it up to 60 again. That's interesting. How about... Why can I not draw now? Oh, okay. An issue could actually be that we override the grid itself. So remember what I said about the buffer? That basically each step gets calculated and then just written to a buffer, and at the end, after each step has been calculated, we actually update the screen. We need to do that in our code, because right here, we modify the grid itself. So what I need here is something like a buffer, and you're gonna have the same dimensions as this. Just basically as our grid, again, just initialized with all zeros. And instead of grid, we write it to this buffer. And at the end of the loop, we just do self.grid equals to the buffer. Okay, now I can draw. Okay. So, okay, let's see if this works. Let's make our glider. Wait, but now I've removed the board, or like the calculated, and now why can I not draw if the board.nextgen is on? Oh, because it always gets overwritten. So what? This is why I did the simulating actually. If board.simulating, then do the next gen. Otherwise, don't do it. So now I can draw, and I can simulate. Okay. That was fast. Let's crank down the frame rate. Do this again. Yeah, see, okay, but now it also gets laggier. I think there actually is a proper way to fix this in Pygame. I'll look into this in a second. But yeah, as you can see, I think I just saw the pattern that we also derived. So yeah, there you go. If we look at our notes, this is exactly the behavior we would expect. And obviously now we could carry on by hand and check the combinations, but I think this looks about right. What I could also check, I'll put up frame rate. Let's go back to the 40 by 40. I actually liked that screen. And maybe let's do the glider there. Yeah. And if I stop the simulation, I can maybe delete it. And maybe let's just do this weird shape. And yeah, that actually looks pretty good. Yeah. We even get the glider like right here. Yeah. And I think if we compare this with the website, again, I'll need to find a spot here. If I do the exact same shape and speed up the simulation a bit. Yeah, it's split up into two, and then we get a glider going down and glider going up. And I think this is the same we get from our code. So if I do this one and run it. Okay, so it runs into the edge here a bit, so maybe that doesn't... Wait. Let's try to do it a bit more central. Okay, I mean the behavior looks about right. We're running into the issues with the edge here, but other than that, it looks fine. Maybe if I increase it to 80 by 80, and I do this, so is it even still? Yeah, okay, it's somehow visible. Yeah, okay, and now it looks right. Now there's the second glider. There is the other one. Yeah, that looks pretty good. Now, one thing I actually want to add is an age mechanic. Now, in many renditions of this game, you actually see that cells that stick around for long. So if I go back to 40 by 40, so there is some stable configurations. Like for example, this always stays the same. So even though I'm simulating here or I have a glider here, this never changes because it's stable configuration. Because again, if you run through the game rules, you'll just see it's stable. And for example, this pixel in the middle is also stable. And I want to kind of show that stability behavior. So I want to introduce an age, and now I'm kind of regretting not having done a cell class. You know what? I'm just quickly gonna make like a cell class. Def init, and it'll last for or like maybe call it state. Is a state, and I'll quickly rewrite all of this logic that we did right now. I don't want to just bore you with all the refactoring. I'll just quickly rewrite this and be back and talk about what we're gonna do. Okay, I think I did it. Okay, no, never mind. Okay, now it looks fine. So okay, so basically I've just rewritten everything to now work with this cell class here. So I just added a state everywhere. Okay, Because now what we could also give it is a self dot maybe an age. And in the beginning, it's gonna have an age of 0. Yeah, it's gonna start with an age of 0. And every time we draw the cell, or like every, let me just collapse all these functions so I can think of it. So basically, I want to increment this age every frame. Where do we do this? Yeah, maybe let's do that next gen. Yeah, because we're gonna have to somehow also give. Yeah, no, we can do this at the next gen. Yeah. So basically, the only way a cell can increase its age is if it stays alive, right here. So right here, we also give it buffer of j of I dot age equals to, well, basically the age the cell had before, so self dot grid of j of I dot age plus 1, plus we increment it by 1. Okay. And now what we need to do is in the draw function, color it accordingly. So it's gray if it's dead, and we'll do a live color. So instead of white, it's going to be some live color. And basically what we need to do is now interpolate between the age and some maximum age. So what we'll do is it's gonna be, well, I think I can just do this. So we'll have 255 times the age dot age. Wait, actually, wait. How do you do a linear interpolate? So it scales with the age, and if the age is 0, I want the cell to be white. So we do a plus 255 here. But if the age is, say, I don't know, 20, let's maybe give it 20 iterations. So if it's wait, give me 1 second. How do you do a linear interpolate? So basically what I want is okay, so we need to do age over 20. So basically if that is 1, I want to have I want to have 100 and not have 255. And we're just gonna have it like this. So actually I want it to be now in the channels. Yeah, no, these channels should decrease and this should be at 255. Also, what we need to do here is cap the age at 20. So wait, in the next gen, where we add the age, we do the min between 20 and whatever that age is. Or do we do, no, we do the minimum? Yeah, right. We do the minimum. So it's at least 20. Yeah, okay. All right, let's actually just see if it works. Int object is not callable. What is not callable? Yeah, I need that. So I do the. Oh, yeah. There you go. Okay, I think this looks fine. So maybe let's again let's remove these cells. Okay, okay. I've already found the bug. Wonderful. But let's actually just see, because I think this produces a few stable. Yeah, there you see it's. And as they get older, they get more blue. Okay, but we've already actually run into a bug. The cell actually remembers its age when it's recreated. So down here, where we create the board, we also grid of y and x dot age. We set it to we just reset it to 0. And I think this should actually fix the bug. So if I do this, and there we have a stable configuration. If I delete it, and yeah, we get back the original age. Okay, I think this is actually all that I wanted to cover today. Oh yeah, and here we found another stable configuration. Okay, and yeah, this is actually, I think, pretty much all that I wanted to cover in this video today. We did recreate the game of life with all its components. Obviously, now you could build on this idea. You could introduce something like, oh wait, I can even, how did I just, oh wow, I can draw with the middle mouse as well. Looks interesting. Anyway, getting distracted. Now you could expand on this. Now see here on this website, it's way more fleshed out. You can have a zoom, infinite worlds, or even a loop around. Because right now these cells at the edge, they're almost always doomed because they just have less chances for neighbors, so they're just gonna die. We could also have the kind of loops around the world itself. Again, I'm not gonna do that. I'm very happy. I'm also actually surprised how well the age mechanic looks here with the, even though it was a very, very like rudimentary or quick implementation. But yeah, I hope you enjoyed this bit of as I said, a bit of a different kind of video. I'm going to be making a couple of more of them. I, again, already have some projects I do want to tackle. So yeah, I hope to see you in the next video.